Hello everyone, my name is Andrew Mattson. I'm taking Math A251 with Dr. Graham, and I'm going to be, for my final project, explaining to all of you rocket science. And I'm going to be tying this rocket science into a few concepts we learned in class, including integrals and the rule of integrating logs. And then, of course, rule of logs. So, what are we seeing right now? What is this up on the screen? Well, we have a spreadsheet, which is kind of scary looking, and then we have a game called Kerbal Space Program. And here on the left, I have just a simple single-stage rocket that I built so that we have some numbers to work with. Okay, so what I plan to show you today is how we calculate something called DeltaV in rocketry. So, DeltaV is the change in velocity over time of, in this case, a rocket. And this is important in rockets because DeltaV tells us how fast we can go. It tells us, with our fuel, how fast will we be able to go at the end of burning all of our fuel. So we can use this to figure out if we can make it to certain orbits, if we can make it to other planets. So it's very useful for determining whether we have the fuel to get somewhere. Okay, so what exactly do we have in this spreadsheet? Here's our full mass. This is when our fuel tanks are full. And here's our empty mass, our final mass, which is when we burned up all of our fuel. And these are in tons, or thousands of kilograms. And here's our constants. So this is the gravity of the planet Kerbin, which is the one that we'll be taking off from in this game. Here's our thrust of our engine, which we're going to be using maximum thrust, which we're going to also be using the vacuum thrust, which I'm not going to get into details there. But that's 1,000 kilonewtons of thrust. And our burn time, which I figured out just by counting how long it took, is about 24.7 seconds total for burn time. So what can we do with this information? Well, I want to figure out DeltaV. So to do that, we have a way to go. First, we're going to go with calculating acceleration. So acceleration, in this case, is going to be, by Newton's law, force equals mass times acceleration. So that means acceleration equals force over mass. So we, with the magic of spreadsheets, can plug in our force over our full mass, and we get this value right here. Okay, so moving up our list, what is this TWR? TWR is the thrust to weight ratio, and this is important in rockets because this tells us how much our rocket, because of the weight of the rocket, will accelerate, and it sort of gives us that number. So the value of that is going to be our acceleration, using the magic of spreadsheets again, over our gravitational force. And that gives us 7.42. And if we look in the bottom of our Kerbal Space Program window there, we have a TWR, which is 7.43. Very close to what we have. We actually have a more precise number, which means we're on the right track. So, DeltaV is the total acceleration over time. And the total acceleration over time, we have acceleration and we have our burn time, right? So you may be thinking, why can't we just calculate that now? Let's take our burn time times our acceleration. And as we can see here, if we look at the bottom left of our Kerbal Space Program window, our DeltaV is 2700 and we're getting 1800. And that is wrong. So the reason for that is we are only taking our initial acceleration and we're missing so many points. Okay, so like I was saying, we're missing a lot of points. How are we going to come up with these points? How about we figure out multiple points over time? So if I make a time, mass, and acceleration chart here, starting at time 0, our mass will be equal to our full mass, so I'm going to be, with the magic of spreadsheets again, putting that in here. Our acceleration is going to be our force, which, using the magic of spreadsheets once more, is E3, over our mass, which is just this value here. So, now we can go ahead and move into our next one. So this will get a lot faster here in a second, because we can do, again, more spreadsheet magic. +1. Here we go. There's our time, our mass. So, of course, our mass, because we're burning fuel, we're going to be changing our mass over time. And our change in mass over time can also be stated as our delta M. So, one way to calculate delta M is to take our initial mass minus our final mass over the burn time. So, initial mass minus final mass is going to be our total mass burned over this time. So let's go ahead and using the power of spreadsheets once more. Okay, so here we have it put in our total mass over the time, and we see our delta mass is about 0.324. Okay, so with our delta mass, we can now figure out, because we divided it by our total burn time, this is how much we burn in a second. Of course, our time is going to be in seconds, so this mass will equal our previous mass minus our delta M, which is B7, like so. And here we have our change in mass. So now that we have that, using the power of spreadsheets again, we can see that our acceleration into the future has changed just a little bit. And again, using the power of spreadsheets, we can figure out that if we go down to our 24th row here, because we go to 24.7 seconds total, here is our final acceleration. Of course, our acceleration increases over time because we're losing mass over time, but the force will stay the same. So you're pushing less and less weight as you move forward in time. So we don't know our delta V yet. That's what our goal was here. But each point in here is the acceleration at that current second. So by adding all of these up, we can get our final total velocity over time, which is our delta V. So let's go ahead and make another one here. Velocity. Of course, our velocity is going to start out equal to just this, like so. And then this is going to equal our previous row plus the row to our left. Here we have that value. Dragging again with the power of spreadsheets, we get 2701.4, which, comparing to Kerbal Space Program, is pretty close. We have 27.02, we almost are there, we're off by 1. Of course, we'll never get a perfect value, but this value here is going to be our OK delta V. And why am I saying this is our OK delta V? Well, we only calculated this at 24 points. The problem with doing something like that is we don't have all of the points under the curve, and I will show if we graph this right here. Insert a chart. Okay, so here we have our little graph. As we can see, here is our acceleration over time. Now this area underneath is essentially what we were calculating with this, but we only calculated at 24 points, and it's a very approximate value. The fact that we got to 2701, which is so close, is just sort of a random chance. So, how do we get more precise here? How do we calculate the area under a curve? Well, this is where we relate back to calculus, and we can switch over to our paper. So, here on paper, we see a few different things. Of course, we see our force equals mass times acceleration equation that I was explaining before, and we have a whole bunch of other equations. So what is this? This is our limit, of course, as delta t approaches 0, so as our change in time approaches 0. We have p, which is momentum, p2, so our final momentum minus our initial momentum, so this will be our total momentum, over our change in time. Okay, so our initial momentum is going to be our total mass times the current velocity, which is what this is, the current velocity, initial velocity. Our final momentum is going to be the mass times our final velocity plus the velocity of the exhaust relative to the rocket, which is what this explains here. So, with all this stuff, how are we going to get to our delta V? So, what we can do is first, given this equation here, what we can do is find what P2 minus P1 equals. So we have P2 and P1 here, so we can go ahead and write these out. And actually what we're going to do here is, because we have this, we can just put in V minus VE, like so, and then minus our quantity of V times M plus delta M. So, now it's just simple algebra. We can carry these out and get mv plus delta V plus delta M V minus delta M VE minus VM minus V delta M. So here a few things cancel out. The delta MVs cancel out. the VMs cancel out. Okay, I made a little mistake. I forgot to put in an M here, but then we are left with M delta V minus delta M VE, which of course is our exhaust velocity. So from this point, we can plug this back into our limit equation, which is going to be delta T approaches 0 of, it was P2 minus P1 over T. Now that we have this, we can do M delta V minus delta, forgot the M in here, delta M VE over delta T. Okay, so from here what I'm going to do is I'm going to separate out the denominators over delta T minus delta M VE over delta T. Okay, so what exactly are we going to be doing with this? So, going back to this equation, this is actually one of Newton's laws, which this is the sum of our total force. So since this is equal to the sum of our total force, we're taking our end momentum minus our initial momentum, which means this has to equal 0 because of the conservation of linear momentum. So if you don't really know what I'm talking about, this is just one of Newton's laws, conservation of linear momentum. I'm not going to go too into the subject, but that is what it is. Okay, so here I'm going to be just rewriting a few things and changing a little bit of stuff, getting rid of our limit, making things a little bit cleaner. So these are constants, our M and our VE, so we can pull these out front, M, and then we're going to change delta V to dV over dt. So here's where things get a little bit interesting. So since ejecting a positive delta M results in a decrease in mass, our dm is actually going to be equal to our delta M, but negative. So as a result, since this is negative, we're just going to make this plus VE and then dm over dt. And because of the law of conservation of momentum, Newton's law, this we know will equal 0. So since we know that these are now equal to 0, we can do a little bit of algebra. dv over dt equals negative VE dm dt. And then even more, we can say dv dt, which is going to be our delta V in the end, is equal to 1 over m times, actually I'm going to rewrite this a little bit better so that we can pull our constant out front. Negative velocity times our 1 over mass, because we're pulling that to this side, times dm over dt. So now we are actually going to get into the calculus side of things, which was the entire point of what I'm doing. This is where things get a little bit weird. We know that we're starting with a velocity. This is our delta velocity, or dv, which is our velocity. So we know we start at our initial velocity, and we're going to end at v plus delta v, which is our change in velocity, which is our final velocity. So, because we know we're going to start at v and go to v plus delta v, we can integrate over that. So, starting at v, going to v plus delta v of dv, and we can get rid of our delta t here, equals, pull out our constant, negative ve, and same thing here, but since we have dm, guess what? At the same time this is happening, that we're going from v, our initial velocity, to our final velocity, we're also going from our initial mass to our final mass. So as a result, we can start at our initial mass and go to our final mass, which is m plus delta m. And of course we can plug in our same thing here. We're going to get rid of our delta t again, because these are our times now. We have from this time to this time, from this time to this time. So integrating now, we are left with simply delta v equals, of course, the negative ve, and this is going to be integration of logs, which we just recently learned, which is going to give us ln of the absolute value of m, and we're going to be integrating that from m to m plus delta m. So I'm actually going to continue this up here. So our delta v equals our negative velocity times. So now we're going to implement our definite integral, and we're going to subtract the small from the big, of course, that's how we do it. So we're going to get the natural log of the absolute value of m plus delta m minus the natural log of m. So we're going to do a little bit more simplifying. We're going to take this negative and distribute it through these. So we're going to get our velocity times, and we're just going to pull this out front. So ln of m And we know these are going to be positive, so I'm going to get rid of the absolute values now, minus the ln of m plus delta m. So using the rule of logs, which is that if two logs subtract from each other, we can take that quantity inside and divide. So delta V equals our exhaust velocity times the natural log of m over m plus delta m, which can be rewritten as delta V equals VE times the natural log of our initial mass over our final mass. So we have delta V here, we have this here. Let's see if this will work in getting us a good value. Okay, so moving back into our spreadsheet, one thing that I did not solve for that is in our equation is the exhaust velocity. The exhaust velocity is going to be our thrust, so we'll go ahead and put this in, our thrust over our change in mass over time. We're losing this much mass over time. We take that and put it over our thrust, and that's going to give us our exhaust velocity with that amount of mass every second, and we get that value. And of course, that's going to stay constant. So let's go ahead and plug in the equation we just solved for. So we're going to get our exhaust velocity times the natural log, right here, of our initial mass over our final mass. And let's see what we get. 2700.2. If we look back at Kerbal Space Program again, that bottom left, 2702 is what we had for our delta V, and this is what we get for our delta V here, which is extremely close, using that equation that we got. And like I was saying, that equation, essentially what we're doing is we're finding the area under this acceleration graph, which is going to be more precise than what we did here with just a few points. Okay, so the equation that we got, going back to our piece of paper, was our exhaust velocity times the natural log of the initial mass over the final mass. For some of you who know rocketry pretty well, you may recognize this equation, and I have down here the rocket equation. Of course, that's a pretty good name for this. So the delta V is the velocity times the natural log of the initial velocity over, or initial mass over the final mass. That's exactly what we got. All I did today was solve for it. How about we have some fun and see what our rocket can do? Of course, some of the values in this are going to be different because Kerbal Space Program itself takes into account the atmospheric drag and many other factors. So Kerbal Space Program says we only have 2400 meters a second of delta V. I'm going to max out our throttle here and take off. We're accelerating very, very quickly. Of course, over time, as we burn more mass, we're going to accelerate quicker and quicker because our thrust is staying the same. I'm not trying to put us into an orbit. I'm just going straight up, which is not how you get into orbit. As you can see here, this is our current orbit around the planet. Since we went straight up, we're just going to go up until we get to that apoapsis here, our apogee, and then we are going to fall straight back down to the planet. Okay, so I've now cut to a point where we are at the end of our apogee. Of course, the planet has rotated underneath us, so we, instead of landing over here, we are landing actually behind where we were set to land before. Since we went straight up, we're now coming straight down, and we are going to be going extremely quickly. So we are now re-entering the atmosphere. We have no heat shields. Our parachute will not be able to be deployed because we're moving way too fast, and we get to see a beautiful explosion as we burn up in the atmosphere, and possibly even collide with the planet. More explosions, and there we go. We have been disintegrated. I hope you learned something today from what I showed you, and thank you for your time. Have a great winter break.